Welcome to educator.com. Today we're going to talk about samples and really about cases, variables, and measurements within samples. All right, so we need to talk about samples because statistics is all about data, and data is made up of cases, right? So each individual that is part of that data set is called a case. And cases are actually made up of variables. You could think of variables as different characteristics within a case. And a variable can take on different values, right? So just to give you an example, here's a data set that's really simple. We have three cases, right? Three shapes, right? And they have different variables. You could think of these almost as dimensions, right? So dimensions of shape, color, area, right? And so these variables right up here these can actually have different values. For instance, triangle is the value for this case, for this variable of shape. For this case, square is the value for the variable of shape. And circle is the value for the variable shape for this case, right? So a variable can take on different values. And because of that, it's called a variable because it could vary, right? Now, it doesn't have to vary. For instance, take a look at color right here. This is a variable that has all of the same values, teal, 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 right? And so although they don't have to, in a variable, the values don't have to vary, they can, right? So we could put a red case in there and it's okay. All right, one thing to note is that regardless of data sets, oftentimes you'll see cases listed in rows. So often each row is a case. Also, often each column is a variable. And you'll learn about different kinds of variables as we go on. So when you look at columns, you see variables. When you look at entire rows, you see cases. Not only that, but when you look at a cell is a combination of a particular row and a particular column. When you look at a cell, that cell often contains a value. So sort of next to cases, variables, and values, as a small note about where they might be in space, you might say usually in rows. This one is usually in columns. And values are usually in cells. Now, this doesn't always have to be the case, but usually by convention, many data sets are organized like this. So we could look here. Here, the cases seem to be made up of individuals. Here, the individuals are taken from Facebook. And the variables are things like gender, friends, siblings, and number of tagged photos. Now, tagged photos by itself is a variable. It could vary. There's lots of different values that it could hold. For instance, 24, 142, 21. So these are different values that could be sort of sitting in the place of the variable tagged photo. Getting data, the process of getting new data is called research. And often research is taught with the 5 scientific steps, asking a question, coming up with a hypothesis, coming up with a design, research analysis, as well as coming up with a conclusion that sort of addresses that question. Now, in order to sort of reframe this scientific, the 5 steps of science, so that it relates more to statistics, I'm going to talk about these things in terms of variables and cases, because that's what's involved in statistics. So research will be about how to get the sample, right? So already we are putting in our statistics terms, how to get the sample. The research question is often a proposed relationship among variables. And a hypothesis often goes with that. So it says, yes, I do think this is the relationship, or I think there's another relationship, right? So these often go together. The research design is the procedure that we use for actually collecting the data. And measurement is actually the process for gathering quantitative information that represents some variable or variables. Let's say the quantitative values, just to use those same words, values that represent or variables. Okay. So here, we're talking about how to actually get the sample. We're looking at proposed relationships among variables within those cases. So research design is all about the procedure for actually collecting that data. Measurement is about gathering quantitative values that represent some variables, right? And research analysis is what we often think of when we think of statistical analysis. So I put statistics right here. And here in statistics, their statistical analysis is going to have its own statistical question and hypothesis. It's also going to have statistical procedures. And you're going to be able to come up with a statistical conclusion. Often this little mini set is often called hypothesis testing. We'll get to that when we talk about inferential statistics towards the middle and latter end of the course. And finally, the research conclusion is going to be different than the statistical conclusion. Here in the research conclusion, we step out again and go back to how this analysis relates to this overall research question, right? So this is the general conclusion. And this general conclusion is created from the statistical conclusion, as well as, considering sort of all that came ahead of you. All right, so what kinds of variables are there? If our research question and our hypotheses are all going to be made up of variables, we better try to figure out, hey, what kind of variables could there be? Well, there's a couple of different variables that you need to know. One we already covered. This one is not really a variable. It's sort of right outside the border of variable, but it's related. A constant is a characteristic that cannot vary in the data set. So for whatever reason, it cannot vary. But other than that, there are two kinds of variables you need to know. One is discrete variables. And when we talk about discreteness, we're talking about things that have very particular values. So when you think about a number line, there are only certain places that can contribute a value to a discrete variable. So these are the only values sort of allowed in a discrete variable. So examples might be something like number of siblings. You may wish you had only 1.5 siblings, but that's actually not possible, usually. So number of siblings is what we think of as a discrete variable. You either have 1 or 2. You rarely have 1.65 or 1.82 number of siblings. Also, another example might be number of gold medals. 1 in the Olympics. So often people don't win just half a medal or 1/8 of a medal or 5 2/6 of a medal. Instead, they win whole medals. So there's only particular places on the number line that can contribute values to these variables. So these are examples of discrete variables. Continuous variables are sort of exactly the opposite. So we might have these, whole numbers like 1, 2, 3, 4, but when you have a continuous variable, you could have this be the value, or you could have this be the value, or the one right next to it as the value, or over here as the value. Any of these values can contribute to the variable. So one way you might want to think of this is that there are no gaps on the scale. So any value can contribute, can be part of this variable. In discrete variables, only certain values can take part in this variable. So examples of continuous variables, are things like length, weight, right? These are values that could have any number. So it doesn't have to be 100 or 101. It could be 100.1 or 100.001 or 100.0001, right? So there is an infinite, even between, let's say, 0 and 1, there's an infinite number of values that could contribute to a continuous variable, such as length or weight. Other possibilities are more abstract. Things like anxiety level or knowledge of history, right? Because somebody could be maybe right here in terms of anxiety level, but someone else could be very close, but just a smidge less anxious than them, right? So these are what are thought of as continuous variables because any value is actually possible. But here's the thing. We can't actually quite get variables in the world. We can't get that truth. Instead, we have to measure it. And often measurements are almost all discrete, right? When you actually measure something, we often round. For instance, when we measure height, we don't measure it to the 0.0001 inch or centimeter. Instead, we often round to the nearest whole unit. So often people don't say, oh, I'm 5'6" and 3/75 of an inch, So often people don't say that. And so because of that, most measurements, our actual skill of getting values of the variables, those end up turning all variables into discrete variables. But underlying the variable, it doesn't have to be discrete, just because we measure it in that way. So when a variable is measured, you'll end up with a particular set of numerical values. And that's often what we think of as our sample distribution, our scatter of numbers, right? And so it often helps to ask ourselves, what kind of scale is it on? I mean, it's all going to sort of be discrete, but there are different levels of informativeness that measurement scales can give us. So let me give you some examples. Well, one reason that it might be helpful to think about what kind of measurement scale a piece of data is on is because it helps us compare pieces of data. For instance, could we look at a number of friends and compare that to ranking in class? Well, those numbers actually stand for very, very different ideas. And that's what we mean by measurement scale. What does the number mean? What kind of information does it give us? So when we think of something like gender, here we're using a number 1 and a number 2, but are we really saying that somehow 2 males, if you add them together, you get a female? Is that what we're really saying? No, not really. These numbers are really just stand-ins for other ideas, right? Whereas when we're talking about number of friends, if we had somebody who has 48 friends, we really do mean they have approximately 1/4 of the friends that the second person has. And can we compare ranking in class? So is this person somehow better than this person? How do we compare, right? And so it also often helps to know what kind of measurement scale we're working with. There are 4 different kinds of measurement scales you need to know. Here they are: nominal, ordinal, interval, and ratio. And I've listed them in an order where they become progressively more informative. So there's more and more information as we sort of go down. And so these are the types of scales you might run into. Nominal scales often are referred to as dummy codes, because nominal scales are really just numbers that stand for names. They look on the surface like numbers, but really they're just names. And the numbers don't actually have any meaning. So there's no meaning in the number. They just stand in, like a dummy, for a name or a category, right? So nominal scales, nominal stands for the idea name, right? You could think of this as a qualitative scale. There's no order. Some examples might be things like color of eyes, right? There's no order. It's not that blue has to go before brown or green has to come after brown, right? There's no particular order to it. Another idea that's a nominal scale is political affiliation or type of major. Those are nominal scales because it's not that there's any inherent order. Even if we assign numbers to it, the numbers are just arbitrary. They don't actually mean anything. Things like type of cheese, state that you come from, what language you speak. Those are all examples of nominal measurements. Okay. So the second level you could think of measurement has a little bit more information. So it's no longer just a stand-in. Here we now have an order. So the numbers actually tell you about order, but they may have uneven intervals. So number 1 and number 2 aren't the same distance apart as number 2 and number 3. A good example of this is Olympic gold medal, silver medal, and bronze medal. So when we think of gold medal, silver medal, and bronze medal, and let's think of this as how the long jump, so long jump. The gold medal may have jumped this far. The silver medal may have been very close, but the bronze medal may have been far off, right? But when they actually get their medals, you can't tell how far off each one was. You don't know whether the intervals are the same or different. So here we preserve order. So now when we know the number 1 and number 2, we know that number 1 definitely comes before number 2. But we don't actually know the interval distance between them. So other examples of ordinal scales are things like your rank in law school. That ranking number doesn't actually tell you how much better someone is than someone else. They might be very, very close, right? But their numbers might say they're 1 apart. Another example, so often examples of things that are ordinal are often rank ordered. So whenever you hear the word rank, that's often an ordinal scale. Also, things like having a master's degree, PhD, or bachelor's degree, those have ordinal scales. They have a sort of order in terms of, I guess, how much schooling you had to do. But they don't necessarily have the same distance between them. Okay, so now we get to interval scales. And remember, I said it's more and more informative as we go down. Now we have order as well, right? But also even intervals. So now the distance between 1 and 2 is the same as the distance between 2 and 3. So when we have interval scales, you might think, wow, like that's like a regular number line, right? Well, there is one thing that this scale is missing. Although it has order and even intervals, there's no meaningful zero. Here's what this means. Usually, when we have a meaningful zero, then that would mean that when we say there's zero of this, what? Then there's literally none of blah, 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 whatever it is. In an interval scale, it's relative. So it really doesn't matter whether you start marking at 1 or whether you start marking at 0 or whether you start marking at 125, right? Let me give you an example that's commonly used, especially in the social sciences. Often when people are asked about their opinion in self-report, they're asked to rate something, so how happy do you feel, on a scale of 1 to 5. 5 being very happy, 1 being not happy. Well, would it have mattered if they had set the scale from 0 to 4 instead, right? So 1, 2, 3, 4, 5 versus 0, 1, 2, 3, 4. Well, you could see that if someone marks a 5 on the scale and someone marks a 4 on the scale, it's not that this person is less happy. They're the ones who are maximally happy, right? It's just that they had a different scale that they were using. So these are examples of interval scales where the 0 actually doesn't mean 0 of happiness. It's just whatever it is relative to the scale that you are using. So that's what we mean by no meaningful zero. You can often test for yourself whether something is an interval scale by sort of moving the scale a little bit and seeing if it's still okay, right? Then if it's okay, then you know you have an interval scale. So let's say you get something like another survey question that says, how satisfied are you with your job? Rated on a scale of 0 to 100, right? Well, if it was on a scale of 100 to 200, would it make any big difference? Not really, right? And so that's how you know that it's an interval scale. All right, so finally, we get to the creme de la creme. So this is the highest level, and if interval is missing a meaningful zero, I bet you can guess what ratio has. So here we have order, we have even intervals, and we have a meaningful zero. So in this case, these are ratio scales are often things like height or weight, where 0 really means 0, none of something, none of some unit, right? So if you are 0 inches tall, that means you are 0, you know, so that really means 0, right? So, so that's the big difference between nominal, ordinal, interval, and ratio scales. All right, so now let's look at some examples to sort of exercise these concepts. So here we have preschool, elementary, junior high, high school, college, and graduate school form what kind of scale? Well, let's see. Preschool, elementary school, junior high, senior high, college, graduate school, they have an order, right? So order. Check. Is there even intervals? Well, not really. The difference between preschool and elementary school, so preschool might take maybe 2 years, and elementary school might take like 6 years, right? So even there alone, we could see, oh, they actually take different intervals. Junior high might be 2 to 3 years, high school is probably 4 years, college 4 years-ish, graduate school, that could be anywhere from 2 to 10 years, right? So, so this definitely doesn't seem like they have even intervals. And because of that, even if we assign these things a number like 1, 2, 3, 4, 5, 6, it wouldn't be that if you subtracted 1, it would be really 0, right? And so I would say there's no real 0 either. So because it does have order, let's go with ordinal scale. Example 2. In one state, voters register as Republican, Democrat, or Independent. Which scale of measurement is used? Well, here, is there an order to this, like there was for the schooling? Well, not really. You may have a different opinion depending on your political leanings, but not really. These are just different categories of people. So I would say that this is a nominal scale. Even if we assign numbers to it, they would be purely symbolic. So example 3, a math professor gives his students a 30-item test on the first day to ascertain his students' basic math knowledge. Bob got a 0, Joe got a 10, Carlos a 20, and Nate and Layla got a perfect score. What kind of a scale of measurement is this? Well, 0 actually does sort of mean something if you think about it as how many items they got correctly, and getting 1 item correct versus 2 item correct, does that really ascertain their basic math knowledge? Well, let's separate it out into first, basic math knowledge. So basic math knowledge is the actual variable that this professor is interested in. And basic math knowledge is a continuous variable. Right? Somebody could have just a smidge more or just a smidge less than someone else, right? So every value can be covered. But in order to get the values for this variable, they used a certain kind of measurement, or he used a certain kind of measurement. And the measurement tool he used was this 30-item test, right? So the 30-item test, what kind of measurement scale is this on? Well, I would say it does have a true 0. 0 does mean something. You got 0 items correct. It does have even intervals. So when you're counting, like, how many questions correct. And you know that, 30 is better than 20 is better than 10. So it has order. And so I would say that this is a ratio scale. However, just because it's a ratio scale doesn't mean that it actually measures basic math knowledge in a really precise way. After all, someone who has a 0 on this test, it may not be that they don't know anything, right? So how it actually matches up to the variable is still up for grabs as a question. But in terms of the measurement scale, it might be a ratio scale. There is one way that it could be, it could not be a ratio scale, and that is this. If the questions are differing levels of difficulty, so there are really difficult questions and really not difficult levels of questions, that could sort of screw us up. But let's just assume right now that all the items are sort of roughly similar levels of difficulty. If so, then I would go with ratio scale. All right, example 4. If the active measurement is disregarded, which of the following variables are fundamentally discrete and which are continuous? Well, temperature is probably continuous because you could be a little bit hotter, a little bit more hotter, a little bit hotter than that, right? So every kind of value can be had on that scale. No gaps. Time elapsed. This is also continuous because you could have every small increment of time accounted for. But in gender, I would say this is discrete because you can't have, there's not every single kind of variation in between. Brands of orange juice, I would also say discrete. This actually sounds nominal, right? Size of family, this is also something that's discrete. Again, it's hard to have 2.75 people in the family. merit rating of employees. So how much merit does an employee deserve? I would say fundamentally that's continuous. One employee could be just a little bit better or worse than another employee. They could be very, very close. And in the same way, achievement score in mathematics, that could also be continuous because somebody might be able to achieve just a little bit more in math than someone else. All right, so that's example 4. Thanks for using educator.com.